All right, thanks so much for coming, everybody. My name's Nathan Taylor. As you may have guessed by now, two things in the world that I like are bikes and old Atari computers. I saw someone wearing an Atari shirt somewhere around this morning, so I feel like this is the right conference to give this talk, or at least to keep this aesthetic going. So I'm a software developer based out of the Bay Area. As proof, I offer a picture of me on the Golden Gate Bridge riding my bike. And I spent most of my career doing low-level systems work, say at the hypervisor level or operating system or language runtime level. But right now, I'm working at a CDN called Fastly. The team that I'm on is responsible for the HTTP proxy that serves our customers' cache content to users. So all this like layer 3 and layer 7 stuff is pretty high up the stack for me, relatively speaking. Our software is a highly concurrent, multi-threaded code base. So given that, you can probably guess why a lot of the material that I'm going to present today is close to my heart. So this talk today is about a problem that my team and I faced. The talk is about a thing that we built that solves that problem. But it's also about the things that we needed in our programming toolkit in order to implement that solution given the problem constraints. And it's my hope that you'll be able to use these tools in your day-to-day when faced with similar challenges. So often when folks from Fastly give presentations, the material is about, say, how a global network like ours might be designed, or maybe it's about solving some hard distributed systems problem like how we purge content. For this talk, though, I'd like to zoom into not only a Fastly server deployment, but a single server within that deployment. So everything in this talk is going to be in the context of a single piece of hardware. So given one of those servers, given our cache node, we have, of course, a collection of processes running atop some operating system. And each process is free to dynamically allocate and free memory within its address space. The problem is that there's no general purpose way in our current system for processes A, B, and C to allocate shared memory between themselves. An example why we might want to do this would be storing indices for cache content that lives on solid-state drives. So the thing that we implemented was a persistent shared-state memory allocator called muslab that processes can allocate from alongside their private heaps. How we did this in a scalable and correct way will be the running example through this talk. So the kind of allocator that we implemented is called a slab allocator. A slab is simply a pool of shared memory, and the allocator returns fixed-size objects from that pool. So if we are one of these processes, we can allocate an object by pulling some memory off a slab and returning it to the calling process. And conversely, we can free memory back to the allocator by conceptually pushing objects back onto the slab. The notion of a slab consisting of a sequence of uninitialized elements is called a free list. It's a pretty common data structure in memory management libraries and garbage collectors. And as you may have noticed, it's behaving basically exactly as a stack or other Philo data structure would. So this is fine. So far, we've only looked at it within the context of a single process. A good question to ask is, what happens if we add some concurrency into the mix? What is the right way to reason about the allocator's behavior in the presence of simultaneous concurrent accesses to the free list? I should say that we have tens of thousands of threads running in processes A, B, and C in production, so this is something that we have to think about pretty hard. It's useful to think about the behavior of the allocator in terms of formally defining a protocol that consumes requests and produces responses. Normally, well, maybe if you're like me, when you hear protocol, you think of like a network protocol. But when we implement things, these will mainly be just simply function calls. So our allocation protocol would have the two operations that we expect, object allocation and object freeing. I think we all agree that intuitively, a response should come after a request, but I'm going to go ahead and make this sort of obviously stated for reasons that'll become clear a little bit later. It's also useful to be able to say that allocation requests can't give the same object away twice, nor can you free the same object twice. So now that we've defined this protocol, we can start to talk about how processes can make requests and receive responses over this protocol by using something called an execution history. What an execution history is it defines an ordering of requests and responses of a protocol over time. So, for instance, if we have a thread that allocates and then frees an object just like this, our execution history would consist of an allocation request, a response, followed by a free request and a free response. It's not super interesting when you have just one thread, so let's have threads A and B operate over this protocol. So in this example, thread A issued an allocation request before B, and it just so happens that A also received an allocation request before B did. The notion of visibility is also crucial in execution history. The y-axis implies some sort of x happened before y ordering, but because all these operations are with respect to a shared data structure, y should be able to notice that x took effect is actually the more interesting notion of what the y-axis represents. So in this case, B's allocation is dependent on the fact that A's allocation response preceded it. So hopefully it's not too hard to see that if you have 4 events in an execution history, you have 4 factorial possible permutations of this execution history. However, the protocol that we've defined puts constraints on what constitutes a valid execution history with respect to our allocation. So for instance, we can't have a thread that receives an allocation response before it asked for it, because that breaks causality and is sort of mind-bending to think about. So we say that this is a protocol violation. Let's put it back so I don't have to look at that. By putting constraints on our execution histories, we're able to better reason about the correctness of our system. So now let's think about ways that we can further constrain execution histories to only valid ones. So there's a notion of a sequential history. Sequential history is an execution history where any request is succeeded immediately by a response. So here's an example of a sequential history. Every request, so A allocates a request or sends an allocation request and immediately receives a response. B does the same thing. A issues a free request and receives a B response. Maybe it's a little bit easier to see if I group them like this. So our previous execution history from a couple of slides back was not a sequential history because you remember like A and B had their allocation requests and responses interleaved. What this means in terms of our protocol, or our implementation of the protocol, is that no thread can begin an allocation or a free until the previous thread has succeeded. Did I screw up? I did screw up. I spoiled the joke. Notice that while we can't interleave requests and responses, we can still reorder request-response pairs and still have a valid execution history because every request is still followed by a response. This is worth pointing out because the notion of what are we allowed to reorder and still consider valid is going to become super critical and will be a recurring theme in this talk. So here's some C. This might be how we implement our allocate and free functions. Right now, allocate just pops an object off our shared free list, and free puts it back on. So what do we have to do in order to be able to guarantee sequential history? Well, we can wrap all operations with a lock. Lock-based synchronization is really the canonical solution to sharing memory in a multiprocessor system. Locks are easy to reason about exactly because they serialize. We only need to think about individual concurrent processes now. Because they serialize access to their critical section, which here is operations on the free list, they achieve a means for achieving a sequential history. Okay, so cool. Now let's look at how that lock might be implemented. There are many different ways of implementing a lock, and if you're using a production caliber lock, it's going to be a hybrid of various techniques. But the most instructive kind of lock for this talk is going to be something called a spinlock. So a spinlock loops or spins in an attempt to move the lock from an unlocked state to a locked state. If the lock is already locked, someone has control on the critical section already, and we have to keep spinning. If it's unlocked, though, we can set the state to locked and proceed into the critical section. So the way that we do this is by first reading the locked state, overwriting the locked state with locked, and then saying, was the old value locked, that is to say held by someone else, or unlocked, that is to say held by nobody. This operation is usually implemented with hardware primitives, and I'm going to call a test and set or a fetch and set lock. Unlocking in this scenario is actually pretty easy. All we have to do is write unlocked into the lock. So here's what an implementation might look like in C. We have something called atomic test and set, which we can just consider to be a function right now, that loops. And while it's locked, we just sleep for a little while. And unlock is just that atomic write. So everything looks correct based on what I've told you informally. But is there a way for us to define the correctness of this implementation a little bit more formally? So because an atomic operation is, by definition, indivisible, any atomic operations to the m variable are sequentially consistent among themselves. So that's cool. Now, there are a couple of things to notice here. And this is, now we're getting into sort of the crux of what I hope to tell you today. First, this test and set operation is really embedded in a larger operation between the call to lock, so the lock request, and the lock function returning the lock response. In the case of multiple threads, let's imagine that B has previously held the lock and unlocks it before A tries to acquire it. So right now, these functions over time are totally disjoint. Notice that we have a stronger constraint than sequential consistency here when we think back to our protocol. We're not allowed to execute the atomic request response pairs such that B's store, its unlock, follows A's test and set, its lock, that is. Because that means that A would have succeeded in taking the lock before B released it. If we think back to what we define in terms of our protocol, we say, well, hang on, that doesn't make sense. So if we've concluded that out of the set of all execution histories, there are a subset of those that satisfy the sequential consistency property. And it seems like we're moving towards a subset of those that satisfy an even stricter property, but we don't have a name for it yet. So let me give you a name for that. It happens to be that the term that we're looking for is called Linearize Abul. A linearizable history is a sequential history that additionally states that requests to responses must not be reordered with respect to each other. So given this definition, we might think that there's only one valid execution history here, because if we're not allowed to reorder executions, we have no choice but to stick with this. However, notice that if A enters the lock function in between B's store response and the unlock response, that was a lot of words, so let me do that. If we do this, then we haven't broken the correctness of the protocol. So it seems like there's something clearly special about the store request responses and the task request and response. So what's special about these two operations here? So this is an excerpt from a paper by Leslie Lamport that, as far as I can tell, is credited with coining the term linearizable. In the paper, they're talking about something different. They're talking about enqueuing and dequeuing elements into a concurrent queue. So it's a slightly different example, but what Lamport is telling us here is that it's sufficient for there to be a single atomic moment in our functions where the action is seen to be committed, as opposed to insisting that the entire function itself needs to be atomic. We call these moments linearization points. So in functions that use a lock-based synchronization plan, linearization points would be the lock's critical section. And in the case of the lock itself, it's these hardware-provided atomic primitives. OK, so now that we've convinced ourselves that these linearization points enforce a correctness guarantee with respect to concurrent users for this lock implementation, another question that we can ask ourselves is, how well does it actually perform? So it's right, but is it fast? So the graph I'm going to show you will plot total acquisitions of the lock across n threads. And we see that in the absence of contention, so if there's only one thread just acquiring and releasing, we get pretty good throughput. 90 million acquisitions per second, if I can divide numbers on a stage in front of a crowd of people, is about 10 microseconds per lock acquisition, which is not bad. And in a perfect world, we would hope that the number of acquisitions we can make is independent of the number of threads. However, the moment we add a second thread, the number of acquisitions we can make drops by a factor of 20. And you might not be surprised to learn that this does not get better as we add more and more threads. It's bad enough that we have to go to a logarithmic graph to see exactly how bad it gets. So even with 4 threads containing on the lock, our allocation throughput drops by 2 orders of magnitude. So this will effectively bound the performance of our allocator. And more importantly, it demonstrates an inability to scale. Oh, yes? Yes, good question. So the question was, what is the layout of the process, or what is the layout of the threads? I talk about a little bit about that later on. I should have pushed it sooner. This is a 16-core machine, 2 sockets. Quad core, no hyperthreading. Okay, thanks. So the question is, can we do better? Well, I should hope so, because we're only 20 minutes into a talk, and lunch probably isn't ready yet. So recall that the test and set operation that serves as our linearization point sets the Spinlock to locked every time. So every time we go through the while conditional, we're forced to do an atomic read and write to memory. And if the lock is contended, we're taking a Spinlock that's set to locked and, well, setting it to locked over and over and over again. So this smells like something that we can improve on, because under high contention, we're going to fail to get the lock most of the time. And setting locked to locked, locked to locked, locked to locked seems like a redundant operation. So our lock now looks like this. If we fail the test and set, let's just try a cheaper read of the Spinlock in a loop. Because we're not doing a write in the already locked loop, there's a lot that happens under the hood. But briefly, there are memory caches that don't have to be invalidated because we're not doing a write. And there's less bus contention to inform different threads that state has changed. So the first time that I saw a test and set lock, I was completely 100% convinced that it was wrong. I mean, isn't there a race condition right in front of us? Well, technically, yes. If you look up the definition of a race condition, it is a system behavior where the output of a system is dependent on the sequence and timing of other uncontrollable events, which is what we have here. And yet somehow this seems to be safe. So are races safe? Well, they absolutely can be. This is the punchline that I hope you leave this talk having a bit of a grasp for. Races can be safe. They only become bugs when events occur out of intended order. So how does the test and set lock perform relative to the test and set lock? Does it improve? Well, sort of. The improvement isn't great. We're still not getting good, predictable throughput as contention increases. So another thing that we can do is add a bit of local state and implement a back-off algorithm. So if there's contention on the lock, we snooze for an exponentially increasing amount of time and then try again. So it's not too hard to convince ourselves that this is correct, because it's the same algorithm as the original test and set. The only thing that changes is the number of times we snooze. This might seem problematic for a different reason, because since we're backing off exponentially, maybe we could overshoot the amount of time that we needed to snooze for and end up spinning far longer than we need to, maybe even making things worse. Does that happen? It turns out no, actually. We get better throughput, but there's still this kink in the graph around, I don't know, x equals 2. That's still pretty depressing. Now, we could probably keep going and trying every trick in the lock to build the best lock imaginable, but it kind of feels like we're only changing a coefficient on this exponential decay. In order to understand why, we need to make a quick diversion into something called a progress guarantee. So let's say we have 2 threads and some Spinlock that's visible to both threads. So the top thread enters the function, swaps the state to locked, and then exits. Now let's say the other thread comes in and wants to grab the lock, but of course it can't because the lock has already been locked. Its progress is halted at the snooze call, and how long it has to wait for is completely dependent on how long the top lock holds the lock for. In fact, if you think about it, the top lock is under no obligation to ever be released. So even though the other thread might be trying and failing and trying and failing and trying and failing to grab the lock, there's no guarantee it ever will. We can say that there's contention on the lock, even though no one is trying to acquire it. So a function is lock-free if at all times at least one thread is guaranteed to be making progress with respect to a function. Notice this is different than making progress inside the critical section. This is just with respect to the locking itself. So the top thread wasn't making progress because it had nothing to do with the lock function. It was doing the critical section. And the other thread wasn't making progress because it was just snoozing all the time. This creates an inherent queuing effect where entire threads are stalled at points. And this is what causes, I would argue, the immediate scalability degradation that we saw in our performance graphs. So sadly, I would argue it doesn't matter how fancy our locks are in this case. We can do our best to limit this effect, but there's nothing that we can really do to totally overcome it using this programming model. So we need to look for a different solution to make these operations safe and scalable. Maybe one that satisfies the lock-free criterion that we just defined. So all threads in an allocate or free function should be able to make some notion of forward progress. Or in the very least, be able to say that any thread in an allocation or free function should be able to make forward progress. In fact, maybe we can use some of the techniques that we used to build the lock that surrounded the allocator to actually build the allocator itself. We're going to do this by looking at some non-blocking algorithms. Non-blocking algorithms and data structures are in the world of safe and scalable. They can make guarantees about progress under contention that our old lock implementation simply couldn't. So how do we make our allocator non-blocking? So there's an atomic primitive that we haven't talked about yet that we need in order to build this. It's called compare and swap. I've always thought of this one as a generalization of test and set, and we'll talk in a little bit why that is. But how it works is it takes a value and a pointer. It's going to dereference the pointer and compare those two values for equality. So if the value and the pointer's pointee are different, simply return false. However, if they're equal, we have a third value, a new value. We're going to overwrite the pointer's destination with the new value and then return true. And of course, this has to happen atomically. So this is done in hardware. And because this happens atomically, we can use this as another linearization point in our functions. So I think maybe it's worth spending a couple of spending some time looking at a couple of simple examples of using compare and swap. If I say CAS, that's just the abbreviation for compare and swap. So this is about the simplest one that I can think of. We use compare and swap to increment an integer given a pointer to that integer. I should say that on most hardware that you'll see, there is a dedicated atomic increment instruction, so you probably wouldn't do it this way, but for an example, this is how we would do it with test and set. So we do it in 3 easy steps. We read the value of the pointer into a local variable. We do the difficult and complicated computation, it's very sophisticated, of taking a local variable and adding 1 to that variable and then storing that value in another local variable. And then we swap the pointer's value of I with I plus 1. So here's a slightly more interesting thing to do that's actually not any more complicated in terms of making the operation atomic. So let's say we have a circular buffer with 32 elements, and a shared index into that buffer that we always want to have wrap back to 0 instead of walking off the end of the array. Here, the new I variable is explicitly computed by 2 distinct operations, but overall, the overall structure of how we make this atomic looks the same, and it's just as correct as the previous slide. I said before that compare and swap is a more general version of test and set. I said this because you can implement test and set using compare and swap. Just a fun fact there. So atomic operations that read the current state, modify that state in some way, and then write it back atomically are called read, modify, write primitives. So far we've kind of glossed over the scenario where the CAS returns false, and we have to retry by going back to the top of the loop. So it's worth to spend some time talking about that. So going back to the memory allocator, if we use sort of the do while CAS pattern that we saw in the previous slides, this is what the allocation function might look like in C. So first we read the state of the stack head and its next element. So variables A and B in the source code correspond to elements A and B in the diagram up top. Next, we try and update the head of the stack, which is currently A, to B using the CAS operation. So if we've succeeded, A has been popped off the stack, and the successor is now the head of the list. That's cool. But what happens if the CAS returns false? So if we go back to our color-coded explanations of how CAS works, the CAS returns false at some point in the situation where in between assigning the local variable A from S's head and the cas. In between that time, the head pointer was changed to a different value by a different thread. That's this mysterious yellow element. We don't know what it is. Maybe a free happened, and A is now the second element in the list. Or maybe another allocation happened, A got popped off, and B is now the head of the list, which is funny because that was the first thing that we were trying to do. My friends, I think we have another race on our hands. But just as before, because the cas is a linearization point, we are able to detect that the state of the free pool changed from underneath us because A was a different value when we do the cas. And even though we have to retry, we know that there's some other thread out there that succeeded in the meantime. This makes this a lock-free implementation, in contrast to our implementation with a Spinlock, where we had no choice to spin even though no one else was manipulating the lock, because we know that someone has made progress here, even if in this particular time it wasn't us. Freeing follows a similar strategy. We read the current stack head, assign the current head to the next pointer of the object we were trying to free back into our free list, and then we swap the new object in. Again, if we fail, we go back to the top of the loop and retry. All right, so this is great. We've defined allocation functions in terms of safe concurrent primitives, and we can have tons of threads hammer this stack, and everything will work correctly, right? Well, we still have some time left, so maybe there is a case we have to think about. So let's imagine that this thread is us, and we want to allocate an object. Let's say that this thread, have executed everything up to the cas instruction, so we're just about to do that instruction. Now remember that there are other threads operating on this data structure, right? So it's totally possible for another thread to come in, that's the cyclist underneath, to try and allocate an object. And because we haven't hit that linearization point yet, it's totally fair that that thread could come in and complete. And remember, that's okay. We've changed the state of the free list, but the cas won't let us swap A if it doesn't see A at the head of the list. So the top thread isn't in a case where it'll do something incorrectly. Why don't we play this game again and have another thread come in and do the same thing? All right, so now the bottom thread now owns B. And let's say that the thread that allocated A is done with the object and wants to free it back. It's kind of a convoluted example. But now A is now back into the list. Now let's finally do our cas operation. So the cas operation will say, is A at the head of the list? Yes, it is. OK, swap A for B. The problem is that the successor in the list is no longer B, but it's C. So we've reinserted B into the stack, even though B is now owned by the bottom thread. So B's memory is simultaneously seen to be allocated and freed. This is a classic concurrency bug called the ABA problem. The definition basically reads that a reference is about to be modified by cas, changes from A to B back to A again, and the cas succeeds even though the overall state of the structure has changed. It's worth talking a little bit about workloads, should you be designing lock-free data structures yourself. With a single allocator process operating concurrently with any number of freeing processes, so this would be a multiple producer, single consumer, the ABA problem can't occur. So it's helpful to distinguish the requirements of your workload to determine whether you need to solve the ABA problem at all, because solving it adds memory and time overhead. But for our purposes, because we are multiple producer, multiple consumer, it is something we have to solve. So a common approach is to encode some additional state with the structure. So we've added a number into the slab head called a generation counter. And what it's going to do is keep track of the number of times we've allocated within this free list. So this provides an additional piece of state. So if you imagine if we pop A, push B, and push A again, the generation counter will have changed between A having been popped and A being pushed again. So rather than having local object pointers, we have temporary slab structures. We need that because we're going to use a new compare and swap operation. dcas is what we call a double wide cas that lets us swap two adjacent values in memory. So this assumes that the head and the generation are adjacent in the slab structure definition, but that's just an implementation detail. Basically, dcas lets us compare and swap two things. So this solves the ABA problem, because even though the A pointer would match in the compare and swap, the generation count would have changed. And we said, oh, okay, something's not right here. We have to reread state. Freeing has to stay the same. A free operation only manipulates the head pointer, and any allocation operation manipulates the head pointer and its next value. So there's no B here for us to have an ABA problem with. So there's one final wrench that I would like to throw into the works, because this is the theme of the talk. And the reason why we haven't needed to talk about it yet is that so far I've been silently assuming that we're all working on x86 hardware. And therefore I've been making tacit assumptions about how our concurrent programs will behave as they do on x86. So let's roll back a little bit and look at the allocation and free implementation that uses spinlocks. So given what I've told you, this is all correct. It may not scale super well, but it's correct. Mutual exclusion should be guaranteed. But given that I just said a sentence that begins with, given what I've told you, this is correct, there's clearly more that I have to tell you. So given two threads, can it ever be the case that some ordering of operations would cause two threads to have the same block of memory returned to them? Well, we should hope not. I mean, we have mutual exclusion, so this is clearly not something that should ever happen. However, in the event that you're running on different kinds of architectures, such as ARM or Power or Alpha, the code as we've written may not work. And this is because there's one more thing that we need to add into our allocation of free functions. It's a primitive that orders memory called a memory barrier. So let's say that these functions are going to, these two threads are going to enter the allocation function together. Well, what's happening under the hood, as far as the CPU is concerned, is just a series of instructions. So what we have is the while atomic tas snooze, and then pull the object off the free list. Okay, so I'm going to do a thing. Don't freak out. We're at Surge. I believe in you that this is going to be a cool thing to do. So this is what some ARM assembly might look like. I say might because I'm a C programmer and I'm not an optimizing ARM compiler. But for our purposes, I think this should be sufficiently correct. If you're not used to staring at assembly, don't worry. There's only two parts of this that you need to know about. These three instructions, comprising of load register exclusive, store register exclusive, and a comparison, correspond to our atomic fetch and set. In case you're interested, on ARM and a lot of other risky architectures, we implement atomic primitives using something called load exclusive and conditional store, and that's what this is doing. But semantically, it's the same as a fetch and set. And this thing down here is just in our allocation function. And this reads the head of the slab after the lock function returns. So remember, this part has to be in the critical section, because this is operating on our shared data. So here's a table from Paul McKinley's book about parallel programming. I'll have all citations and a link at the end, so don't worry. Rows correspond to different processor architectures, and columns are the different kinds of way memory instructions can be reordered underneath our feet by the processor. So x86 is pretty restrictive. The only thing that it can do, according to this table, is move a store after an unrelated load. This can actually bite us in a few specific scenarios, so we do need to think about memory barriers on x86. But overall, this is pretty sensible. This isn't going to surprise us in too many ways. So we say that it has a strong memory model. ARM, however, is a lot more permissive in what it's able to reorder. So in particular, notice that ARM is allowed to move the order of unrelated load operations around and can change the relative ordering of loads and even atomic instructions. So this isn't a bug. This isn't incorrect behavior. It's well defined according to the ARM processor manual. And there's a good reason for this. The CPU can make just-in-time memory operation decisions that a static ahead-of-time compiler wouldn't necessarily be able to reason about. It might be able to say, oh, well, these cache lines are already here, so if I move these loads around, memory accesses are going to be more efficient. So that's cool. So if we look at the ARM doc, what it says, the processor can reorder memory accesses to improve efficiency, providing that this does not affect the behavior of the instruction sequence. Well, the problem is that the notion of an instruction sequence is all about how the program behaves in a single-threaded environment. So all we have is this. So from the processor's perspective, because the lock and the free list are totally distinct memory locations from each other, there's nothing preventing them from flipping the order of these loads. And because the memory accesses can be done speculatively, so even before previous reads have succeeded, this reordering can happen even if there's a conditional in between. So from our perspective, what we might possibly observe is this. So this is clearly not what we want. Reordering has pulled the read of the head pointer out of the critical section. So how do we get ourselves out of this mess? What we need to do is draw a line in the sand. We need a way to be able to say any memory operations above this line can be reordered above the CPU, but only up into this line. They can't be moved below. As it turns out, there are instructions to draw such a line in the sand on ARM, and indeed, basically any architecture. In this case, it's called the data memory barrier, and the description, if you can read it, says exactly what we need. All memory accesses before the DMB instruction are completed before any memory accesses after. So by adding memory barriers into our lock and unlock functions, we're able to tell the CPU that there is an inter-thread ordering dependency that it's not allowed to violate. Okay. So now let's show a couple of micro benchmarks of our allocator, where we tried to find the maximum throughput of the allocator. So how many allocation-free pairs can we do in a given run? For reference, these were run on one of Fastly's cache nodes, not while serving traffic, don't worry. It's a 16-core Xeon. And there was a question earlier about what the hardware layout was like. I'll just remind you, it's 16 cores, 2 sockets, so 2 distinct processors. Each processor is a quad core. So in a throughput test, we're going to guarantee proper access to the free list using either our Spinlocks or our CAS operation. So with one thread, it doesn't look like the CAS operation does very well at all. We perform about as well as with locking with pthread mutex, but the test and set locks absolutely smoke us. It seems like maybe because the CAS operation is logically more complicated than a lock's test and set, all of this might be more trouble than it's worth. Well, but when we start running concurrently, when we scale up to a maximum of 16 cores, we find that the concurrent allocator using CompareSwap remains reasonably stable with its throughput as the number of cores increase. Indeed, you can even notice a slight uptick as the number of cores increase, in a small number, going from 22 million allocations to 29 and change. In other words, going from 1 core to 2 lets us do marginally more work, and that sounds pretty great. This is the sort of thing that we want to see with a lock-free algorithm. Even though a CAS fails for us, it's always succeeding for someone else. So even though our throughput doesn't go down the drain as the number of threads try to modify the free list increases. I do want to point out that I'm showing results for pthread mutex here, and we're being really unfair to it. As we all know, when we build production-grade software, there are goals apart from pure performance, and the pthread library has a lot of great features like interoperability with the operating system, bookkeeping, debugging data, fairness guarantees that the Spinlocks don't. So don't take this graph as an apples-to-apples comparison with pthread. I don't want you to leave with the idea that, okay, I need to implement my old test set lock because pthread sucks. I've included it here out of interest's sake, because people invariably ask, well, how does a production caliber lock work here? So let me show you next some stuff about latency distributions. Even though throughput is an important thing to know about, we'd also like to know something about how much variation to expect for an operation to succeed. Because locks don't provide guarantees of progress, we expect a high amount of jitter in how long it takes to acquire a lock. So these numbers are plotted with the top 1% of samples removed and show how long in CPU cycles it took to acquire a lock. I think we ran this we have 1 million samples in here. So even though this is nominally a box and whiskers plot, for test and set, the boxes are all but invisible. So on 16 cores, we see upwards of 300,000 cycles for an allocation using a test and set lock. As I said before, the Linux pthread interface is a great general purpose interface. And notice that because the boxes are taller, this suggests a more even latency distribution. I'd argue because pthreads, as I said, have a notion of fairness in them. But we still see significant variability between our bottom and top quartiles, and further jitter to our max value. Adding exponential backoff, as we saw from earlier graphs, performs better in the worst case. Notice that the y-axis dropped by an order of magnitude, but variance is still super high. And of course, here comes the punchline. Our compare and swap interface behaves extremely predictably, even under high contention load. Our y-scale has dropped by 2 orders of magnitude, and we see very little deviation from our average latency. I feel pretty strongly that having reproducible results is important when giving these kinds of talks. So we put the Alligator and benchmark runners up on GitHub if you're inclined to take a look and play around with the code. So we can only scratch the surface of scalable multiprocessor programming in this talk, I'm afraid. But there's so much more that we want to say if we want the full story. Let me give you 2 things of interest. For instance, I purposefully tried to not bring notions of memory caches, cache coherency, and the memory hierarchy into this discussion. But if we want a detailed picture of what was happening with poor lock performance, we need to understand how main memory racks processor caches and how CPUs synchronize shared memory with each other in order to maintain a globally consistent view of memory. Next, we saw an example of a compare and set operation operating over 2 words of memory. So a question you might have is whether we can extend this to an arbitrarily large region of memory. Well, it turns out that there's much work in a field called transactional memory that might provide a solution to this. It's very much inspired by the notion of a database transaction. We operate concurrently on a shared region of memory, but we have a mechanism to detect when multiple threads have written different values into different parts of that shared memory space. And there's a mechanism to roll back those operations to a safe state. Doing this efficiently in hardware is very much ongoing work. Okay, so let's summarize what we've talked about and maybe entertain a few broader thoughts on the subject. So, safely racing processes is not only common when addressing throughput and latency issues in software, but it's a crucial part of the design process. We've seen how racing waiters on Spinlocks can improve throughput and how our concurrent allocator races protect against the state of the free list head. We also saw how bolting mutual exclusion on top of a sequential lock, that is, abstracting a single threaded data structure behind concurrency primitives, yielded a correct implementation but a slow one, and how scalability was achieved by implementing the stack primitives themselves in terms of lock-free concurrent primitives. The most important theme of the day, as far as I'm concerned, though, is that of linearization and linearization points. Without the property of linearization, all these concurrent stack operations would fail. The linearization points created by using atomic primitives like TAS and CAS can help us prevent race conditions from becoming bugs in our concurrent software. And in general, this is how non-blocking data structures work. You snapshot state, you create a next good state, and attempt to atomically commit the new state. Now, it might be that you're not in the business of having to write your own memory allocator. It might be the case that your software environment, say if you're running on top of the JVM, doesn't even give you the option to manage your memory. It might even be the case that you've never faced the sort of performance problems that a scalable memory allocator would even help you solve in the first place. While all that might be true, let me put forth a few reasons why the material in this talk should be of a broader appeal than just people who write memory management libraries. The most important reason is, in my opinion, that writing high-performance, high-level code is harder than writing high-performance, low-level code. It's because you have to understand the stack at all. You have to understand how the intermediate layers of your stack perform and interact, and arguably are implemented. So now that you've made it through this talk, you could probably take a guess about how Java's atomic integer class or closure's swap functions are implemented, and you might have a better grasp about how they could be used to implement your own software. Further, higher-level languages like Java, and now even C++ with a new standard, have concurrency guarantees through a memory model that may or may not be stricter from what the hardware provides. So if you have a multi-threaded Java program and it's behaving correctly, is it because that the code that you've written corresponds to the Java memory model or the x86 strict memory model? If it's actually the latter, and you move your code from x86 to ARM, will it still run correctly? In case you missed the memo, your computer is actually a distributed system in the small. There's a ton of overlap between what we needed to know about execution histories, different kinds of consistency guarantees, and so forth, in order to start working in a concurrent world. And all of this and more is needed to start working in the distributed world. The final point is entirely subjective, but I think this stuff is interesting and fun. Hopefully you might agree now as well. So forgive me, I couldn't resist doing this. Once a language runtime hacker, always a language runtime hacker, I suppose. That's actually a little hard to read, so if you can't read it, apologies. So if on the last slide you took a guess about how Java's atomic integer implementation might be implemented, well, we can go to the source and take a look. If you didn't make a guess, you have a second and a half to come up with one. We see that it calls into the unsafe class, and it is indeed a compare and swap in a loop. And now what about what about Closure's atoms? This one's nested through two function calls, but hey, look, what do we have? A compare and swap again. Code splunking how Java locks are implemented is an exercise to the listener, if you're interested. Java locks are actually pretty interesting because they wrap p threads but offer some stricter guarantees. So the very last thing I'm going to say is that these slides were made together with my colleague at Fastly, Divano, who's giving a talk on the same material at Strange Loop this week. He may actually be giving it at this very moment. So if you found this material interesting, you should check out his talk when it's posted online, as I'm sure it will be also interesting and informative. That is about all that I have. I will be at the Fastly booth outside if you want to come and say hi. Image credits, code examples, papers and books, all sorts of fun stuff is listed in a README file in that repo. So feel free to check it out if you want additional material. And that's about all I have. So if anyone has any questions, I would be happy to take them now. Yes?
I might have missed it. You were showing the ARM assembly code, and you showed how it had out-of-sequence loads, and then you had a memory barrier. You showed it in assembly. I was wondering, is there a Pragma in C or something so you can construct a compiler?
So the question is, I showed the memory barrier in assembly. Are there primitives in C that will let you do this? The answer is yes. They're usually done in terms of library calls. So often where you will see this is in the internals of the Linux kernel. So Linux has a architecture agnostic atomic read and set functionality that would insert these barriers for you. Additionally, if you're writing user space code, there are libraries like concurrency-kit, which is used pretty heavily internally at Fastly, that lets you set memory barriers yourself. That's a good question. I don't believe so. So to the best of my knowledge, the C standard doesn't specify a memory model. There may be GNU extensions that do it. If there are, it's probably just the same as the one from the Linux kernel. That kind of makes sense. But I've only ever seen it done by way of, a function call that wraps some inline assembly. Yeah, it's worth pointing out that there is an equivalent set of barriers for compiler reordering as well. Yep. So compilers can reorder stuff as well. I didn't talk about that because we're not really talking about compilers, but that's also a thing. Anyone else? Seeing none? All right. Well, in that case, we can go for lunch a little bit early then. Thanks for coming, everybody.